How does the embedded C toolchain work? Imagine turning your simple C code into a tiny, efficient set of instructions that a microcontroller can understand and execute. That's exactly what the embedded C toolchain does. It's a collection of software tools that work together to transform your high-level code into machine language that runs on embedded systems like microcontrollers. The first step involves the compiler. Think of the compiler as a translator that takes your embedded C code and converts it into assembly language specific to the microcontroller you are using. Embedded C is a version of the C language designed for embedded systems, allowing direct hardware control, real-time responses, and efficient use of memory. The compiler handles low-level operations like manipulating bits, accessing memory-mapped registers, and managing interrupts, which are essential in embedded applications. Once the code is in assembly language, the assembler comes into play. Its job is to turn that assembly code into binary machine code, which is a series of zeros and ones that the microcontroller can understand directly. This binary code is what the microcontroller's processor executes to perform tasks like reading sensors or controlling motors. After the assembler creates the machine code, the linker steps in. The linker combines machine code from different source files and libraries into a single executable file. It also resolves references between different parts of the program, making sure everything works together smoothly. The final output is a binary file optimized for size and speed, which is crucial because embedded systems often have limited memory and processing power. Supporting this process are libraries that provide functions to control hardware components like timers, communication interfaces such as Universal Asynchronous Receiver Transmitter, Serial Peripheral Interface, and Inter-Integrated Circuit, as well as support for real-time operating systems and device drivers. These libraries are tailored to specific microcontrollers, making it easier to write code that interacts with hardware without needing to know every detail of the chip. The debugging tools included in the toolchain are vital for testing and troubleshooting. They let developers run the code on actual hardware or an emulator, set breakpoints, step through instructions, and inspect memory and register values. This helps ensure the code runs reliably and meets real-time requirements. From an electrical engineering perspective, the embedded C toolchain enables precise control over hardware resources. It allows programmers to write efficient code for controlling GPIO pins, timers, communication protocols, and handling interrupts. This makes it possible to develop applications for automotive systems, industrial controllers, or consumer electronics that need to operate under strict timing and power constraints. In a typical workflow, you write your embedded C code in an integrated development environment, which integrates all these tools. You compile and link your code into a binary, then flash it onto the microcontroller. Using debugging tools, you verify the code's operation and optimize performance. You might repeat this process several times to get everything just right. In essence, the embedded C toolchain works by taking your high-level code and converting it into optimized machine instructions through compilation, assembly, and linking. It is supported by libraries and debugging tools that help you develop reliable, efficient embedded systems. This entire process is fundamental in creating embedded applications that are fast, reliable, and tailored to specific hardware needs.